Okay, today's video is on crumple zones and what we call crumple zone physics. So what we're going to look at first is what are crumple zones and how do they relate to Newton's second law? So basically, during collisions of objects, and so we use the example of cars, why is it better that a car crumples up rather than remains super rigid during a collision? Why is it when you are trying to reduce your impact against a wall, let's say you're running at a wall, why do you try and cushion yourself from that collision as opposed to just hitting the wall and stopping instantly? Why is it that we have crash mats? Why do we have bungee cords? Why do we have airbags? Why is it that you have cushions on the soles of your shoes? Why is it that you have a trampoline that's very flexible and springy? Why is it okay to jump into a pile of leaves or into a pile of soft snow as opposed to a pile of ice? So these are all really important concepts, and they're all related to something called crumple zone physics. And crumple zone physics is just another way of thinking about Newton's second law and inertia, of course. So we're just reframing Newton's second law and talking about how it can be used in so many different ways throughout, in everyday life. So basically, the technical thing for a crumple zone is a zone of a car that absorbs energy upon impact. Now, it doesn't need to be a car. A crumple zone can be for anything that crumples up, right? And so it's, you can go all the way to like armor in the ancient times where you would wear a steel plate armor and underneath it you would put a lot of padding. The padding was there to one, stop the chafing of the armor, but two, if you got hit really hard with something like a rock or like an axe or something like that, the metal would protect you, but the cushioning of the soft padding underneath would absorb the impact by reducing the forces of impact, and would help save you. So now what we're going to look at is, what is it? So it says the purpose of a crumple zone is to increase the amount of time it takes the car to come to a complete stop, or the amount of time it takes for any collision to occur. Okay? So the key is increasing the amount of time to stop an object. By increasing the time it takes for your car to come to a stop after you hit an object, the force is spread out over a longer period of time. Now, let's take a look at how this might play out. So we know that Newton's second law says that the net force acting on an object is mass times acceleration. We know that acceleration is the change in speed over the change in time. So if you're looking at this equation here, right, if delta t is increased, meaning we increase the collision time, then what we end up with is this denominator gets really big. So if the denominator gets bigger and bigger and bigger, and your change in speed stays the same, so if, like, let's say you're going 5 kilometers an hour and you stopped, your change in speed is just 5 kilometers an hour. But if you increase the amount of time, the acceleration will decrease. Okay, what does this imply? Well, this implies that the impact force, or the net force acting on the object, is decreased. So you get a reduced impact force. The net force required to make you stop becomes less. And therefore, the force of impact is translated into that. Another way to think about this is about the crumple zone, or the distance through which a collision occurs, is to think about it like this. You could say the impact distance is v2 squared minus v1 squared over 2 times the acceleration. And so or we could rearrange this for the acceleration. Let's say v2 squared minus v1 squared over 2 delta d. This is probably a better way to look at it. So if you want to look at this is equation 5, instead of looking at it as the amount of time it takes for a collision to occur, which is one way of thinking about it, look at it this way. If the collision distance, so the crumpling effect of an object, if it gets bigger and bigger and bigger, the denominator gets bigger, your acceleration gets smaller, assuming that your V2 to V1 is the same. So let's say you jump out of a building and you want to land in a crash mat. Well, no matter what you do, your initial speed of jumping out is 0. Your final speed just before you hit the mat is some speed, but you can't change that if you jump out from the same height. However, if you hit a 1 millimeter thick padding, you're going to have a massive acceleration. The time of the collision is going to be very short, meaning if the time of the collision is really small, you're going to get a huge acceleration. Or if the distance is really, really small, your denominator is small, which means that your acceleration is going to be big. Whereas if you hit a mat that collapses over 3 meters, let's say, then all of a sudden you get a bigger denominator and you reduce the amount of acceleration. So, and we're going to use this one quite a bit, this formula right here. And so what you look at is you say that if the displacement or the crumpling amount increases, this causes a decrease in acceleration, which causes a reduction in the force of impact. And this is sort of, this thing here is your crumple zone distance. Okay, and that's going to be coming really handy. This concept's used everywhere. And we're going to look at some videos and just kind of get a sense for it. Now, before we look at the videos about it, let's do a quick little example. And then I'm going to go through a whole series of examples with you in the next video tutorial. So now you're going to want to watch this whole video because the videos that we're going to watch are pretty cool. And then there's a funny one at the end that you're going to enjoy. All right, let's say there's a car traveling at 20 meters per second and lands into a solid wall that does not move at all during the collision. Not a good idea, not a good thing. For the conditions below, determine the acceleration of the force of impact for this. Okay, now move it all in for each of the conditions below. Determine, so that the conditions are going to be on the next page. But what we're going to talk about first is, it's going to crumple over a small distance and crumple over a big distance. You know what? And I think I'll leave this for the next video tutorial. But we're also going to talk about something about calculating G's. Now, you've often heard of something called a G-force. And so the number of G's is calculated by dividing the object's acceleration by the acceleration of gravity. So I just want to show an example. And then we're going to use this in our other. So let's say that you undergo an acceleration. And whether it's a stopping acceleration or a speeding up acceleration. And let's say that your acceleration is 30 meters per second per second. Well, the acceleration of gravity is 9.8 meters per second per second. Okay, some people approximate this just to make life easy to 10 meters per second on the surface of the Earth. So if you want to find out the number of G's that you are experiencing, you would take the 30 divided by the 10, or you can divide it by 9.8, and you would get 3 G's of force. So 3 G's, and so that's saying that it's 3 times the acceleration of gravity. And that's a lot. 3 times the acceleration of gravity is quite a bit, actually. You could have like a half a G. So if your acceleration was only 5 meters per second, and you do 5 divided by 10, you get 0.5 G. So you're pulling half a G of acceleration. It says here, sustained acceleration is over 10 times the acceleration of gravity, or about 100 meters per second, or 980 meters per second, is sustainable, but it can be deadly. So usually in car crashes and stuff like that, you can hit 10 G's of acceleration, but sustained for a long enough period of time, you're going to die. If you ever watch the show Expanse, they undergo G's for an extended period of time, like high levels of G's for very long periods of time, and they have to inject their bodies with like inertial fluids and all this sort of stuff. But if they do it, they actually end up dying from it. So you can only sustain it for a while. And some crashes can occur. You can get over 50 G's of acceleration, which is about 500 meters per second of acceleration, which is deadly. But if you sustain it over a very short period of time, it's sometimes survivable. It's not fun, but it is possible. So you're going to be calculating G's in your lessons, in your work as well. So we'll come back to the examples, but let's watch some of these videos and then we'll take a look at those in a separate video. Okay, so parkour. Parkour is an example where you can use crumple zones. Now watch. What you'll notice them doing every time they're about to land, you will see something. People are nuts. So with all of the stuff they're doing, watch, they will bend their knees when they land. Now, why they're bending their knees when they land is going back to that formula where they want to crumple their legs, which means that they want to increase the distance of their collision so that it reduces the acceleration to a smaller number, which reduces the force of impact. And that's why during any kind of jumping, you don't land and jump with your legs straight. Because if you make that delta D really, really small, meaning like you don't bend your legs at all, you're going to jam your knees and your back and everything. It's going to be very painful. You can break your legs, all that kind of stuff. So people that do parkour understand the principle of crumple zones for their body, and they're able to actually withstand quite high. They can jump from very high distances and do really cool things as long as they're careful to make sure that they increase that distance of collision. And you gotta be a little bit fearless, I think. So you can go back and watch this video, but parkour is one example. Here's another one. Car crashes. Ow. So 80 kilometers an hour. Now, you'll see here that the car crumpled up. Now, cars are made to crumple up nowadays. It's actually safer than the old cars where they didn't crumple. And so you can see that the car used to be over here. Now it's much shorter. And so that delta D is bigger, which means the impact time is longer. And the delta D was bigger, so the accelerations are lower. Cars are also made differently now so that they have a deflector shield kind of situation happening so that the engine doesn't end up in your lap, which is a really bad thing for you. So what the engine does is it drops under the car and goes underneath the chassis away from the people. And then the other parts of the car fly over the top. So the carriage or the interior part stays the same. There. So here you can see all the crumpling. The engine will drop under here. Parts of the car will go up there. But you can see how much that crumpled, probably 1.5 meters or so. Okay. And that will save your life because that will mean that the accelerations that you experience are much less, which means the force of impact is actually reduced. Here we have, because of inertia, the car is stopping, but you're moving forward at the same speed the car was originally going. So you're going to hit your face off of the steering wheel, and it's going to be a mess. So what you do is you get these airbags. Now the airbags, when you hit it, the airbag cushions the blow, meaning that you will not come to a stop instantly on the steering wheel or the glass. You'll have a delta D involved, which means that your accelerations will be lower and you'll not be as damaged as you would be otherwise. Now the kids in the back, they're going to get whiplash still, but so it says to leave them uninjured, more or less, from that. All right, another one, high falls. Okay, so the high falls, and again, you can finish watching that if you want. So watch this guy. He built a box set down at the bottom there of boxes. I would not recommend, do not do this. They're right here, the boxes. This is not advisable ever. And he just landed in a big pile of boxes that he built. There you go. Now, the delta D is big enough that you can withstand it. Obviously not if you land on your neck or anything like that, but he landed flat on his back. And again, do not do this. So you'll see that when he falls, the crumple zone allows him to sustain it. Now, most people don't realize this, but bungee jumping is also a form of collision. During your free fall, you're going to start from a speed of 0. You're going to reach some maximum speed as you're falling. And then what happens is that's your v2 squared minus v1 squared. Then you divide it by 2 delta d. Well, what's the delta d? The delta d is the stretch that you get. If the rope had no stretch, the inertia of your body moving forward is going to tear your legs off. But if there's a delta d and a stretch, the bigger the delta d, the longer the time of the collision, the longer the delta d is, the smaller the acceleration is, which means there's very little actual net force required to slow your body down over that long period of time. This is one of the world's tallest. And again, I would urge you to watch this on your own afterwards. 233 meters. No thanks. I was about to jump, and one of the guys comes and says, "The board's not done right. The other guy did it wrong. Let me fix it." Who knows if that's true? Might be. No, thank you. It's getting ready. Oh, he's almost flying. And it'll start to stretch when it reaches the bottom. And there's the collision. It's stretching now, and that's the collision. Now, you'll see there's a mat. Now, when he's slowing down over that long distance or that long amount of time, it makes the acceleration small, which means the forces his body is feeling is very low. The crash mat at the bottom is quite thick, and when you hit it, it's a big airbag. So if it broke and you fell, you would just hit the bag, and that would be also a big delta D or a long collision time, and you would survive that. Now you're thinking, how could you survive that? Well, think about it. This rope or this bungee cord is going to break probably near the bottom. It's not going to break at the top or on its way down because it's no force on it. When it's at its maximum stretch, like an elastic, you can think, when you stretch it too far, it snaps. So if this one were to break, it would break near the bottom. And if you think about it, as it's going down and stretching, you're actually slowing down. And when you reach the bottom of the stretch, you're actually stopped. So theoretically, if it snapped when you're right at the bottom, you're only a few, maybe 10, 15, 20 meters off the surface of the mat, which means if it broke, you're about 40, 50 feet from the mat, you would just fall into the mat and the mat would break your fall. Now, if you miss the mat, that's a different story. But these don't break very often. In fact, I'm not even sure if there are situations where they have broken. I'm sure it's happened, but it's unlikely. Okay, last one is I've done some bungee jumping many, many years ago when I was young. This is in BC, up near Whistler. You bungee jump off a bridge down into a little gorge with a river underneath. It's a very nice spot. And yes, I screamed. It was horrifying. What an embarrassment. Now listen. He said that was right. That was the loudest scream of the day. Thanks a lot. So anyways, going backwards like that is actually quite scary. And you will, yeah, enjoy that. So bungee jumping is pretty exciting. Give it a shot if you get a chance one day. In a reputable place. So again, the key idea, Newton's second law, acceleration is delta V over delta T. So we want to increase T, the time of the collision, to reduce the acceleration, to reduce the net force. Looking at it as terms of crumple zones, we rearrange this formula for acceleration. We say you're going to change your speed by some amount. If you increase the distance through which you stop, which is increasing the time, your acceleration will drop and you'll get less impact force. That's the key. You should be able to reproduce this and understand this concept very greatly. We then talked about how to calculate G's. In the next tutorial, we're going to do some quick examples and then you're going to finish up the package.